To our first to the session on neutrinos, and also later on in this afternoon, the new infrastructure proposals. Our first speaker of this afternoon is Carla Bonifazi. She's going to tell us about the CONNIE experiment. Carla, I know, are you there? You are there. I will try to warn you when you have a couple of minutes left or so.
Okay,
you have 20
good.
minutes. Thank you.
Okay, can you see my slides, right?
Yes, we can.
Okay, good. I will start them. So this is an update on the future of the CONNIE experiment. So let me remind you that CONNIE is an international collaboration with about 35 members from 6 countries, mainly from Argentina, Brazil, Mexico, Paraguay, Switzerland, and US. And our main goals are to detect the seventh that I will explain in a while. The seventh interaction from neutrino from nuclear power reactors, and then to explore also physics beyond the standard model and develop an alternative method to monitor a power reactor for subaward purposes. So as you may know, seventh is coherent elastic neutrino-nucleus scattering. We use this acronym just not to tell all this large word. The idea is that it's an interaction that was predicted by the standard model more than 40 years ago, but very difficult to detect. It was measured for the first time by the Coherent collaboration in 2017. And the idea is that the neutrino will scatter the nucleus as a single particle. So we will have the recoil of the nucleus, and this is what we try to measure. This is a dominant process for low energy neutrinos below 50 MeV, and the cross-section is increased thanks to the coherent elastic interaction and depends of the square root of the power to the number of the neutrons in the nucleus. So this is very important because with this interaction, we don't need to have huge detectors because the cross-section get at least a factor 100 enhanced, as you can see in this plot, and also has not a energy threshold as the inverse beta decays has, and this inverse beta decays the interaction that neutrinos experiments used to use for neutrino detection. So this will allow us to explore the very low energy spectrum from the power plant. What I already said, that it is very hard to observe, as you can see, since the recoil energy is very small. Is in the level of the threshold of most of the detector, that is a few kilo electron volt. But thanks to the development of new technology for dark matter detection mainly, now we can have access to this low energy with some of those technology as silico detectors, German detectors, some argon detectors, etc. So why we want to detect 7? First, because we can study a fundamental interaction of the neutrinos. Also, we can measure the cross-section and also Weinberg angulus. I put some examples here, so there's a lot of literature. And then we have a way to explore the new physics, and we have a lot of non-standard interactions and a lot of neutrino properties, light vector mediations, etc., etc. So you can see that there's an broad number of models that we can explore by measure sevens. Also, we can have some information about nuclear physics, like form factor, and the neutron distribution radius. Also, sevens is a background for dark matter experiment, is what we have the neutrino floor. And as maybe you know, recently Xenon collaboration measured neutrinos, solar neutrinos by sevens interaction. So also by sevens, we can improve our models about supernova since the neutrino carrier of the energy. And also since sevens does not depend on the neutrino flavor, we can have a chance to detect with more statistics neutrino supernova in our tone scale dark matter detectors. And also, as I said, reactor physics is very important to monitor the fluxes in the reactor, how the fuel is used in the reactor. We have access to an energy range where we cannot measure with the other kind of interaction. And also, there's a lot of prospect to use these detectors for non-proliferation nuclear weapons. So this is a worry scenario where we have a lot of efforts, some ongoing experiments, some project experiments, neutrino experiment in stopped pure beams, or also in nuclear reactors. And these results we can see here in Brazil, CONNIE, and also in Argentina. We have another experiment with the same technology of CONNIE, that is Atuchan. You will have more information tomorrow. So this is a neutrino experiment. We have a neutrino facility that is a container where we sit the experiment. It's 13 meters for the 4 gigawatt reactor core. This power plant has 1 month of reactor off, where we can measure our background each 14 months approximately. At the site, we have a flux of 10 to the 12 neutrino per centimeter square per second, just to shield the experiment. We use a passive shield here, you can see, with lead and polyethylene, and we reach an energy threshold of 15 eV. That is a new goal of the experiment. So what we use to detect that are CCD, silicon detectors, pixel size, where I will not go in details on how this CCD works, but basically we can create electron holes pairs when the neutrino recoil, and then we can collect the charge and then read it. So next one. It's not moving now. Okay. So just to context a little our 10 years of detection now, we have the first idea much before than 10 years ago, that it was in 2010. And the idea is that to make use CCD that were being used for dark matter detection as a starting for neutrino detector, and our partnership, ν-Angra neutrino experiment, already installed a container where they have room to place us, as you can see here. And up to now, you have these 2 experiments with a lot of synergy in what is infrastructure and maintenance of the new lab. This is the name we gave to the facility. So then we start to make background measurements and to work on the infrastructure to be able to install the experiment. And finally, we installed the experiment at the end of 2014. We will have 10 years, as I say. And we have a small sensor just to prove the concept. And we published our first result in 2016, showing that the experiment was possible. And this allows us to make an upgrade, install a significant more mass neutrino sensor, CCD sensor. Here you can see a picture. And with the first run, or with those sensors, we can show that we can put a limit to the reactor on minus reactor off rate, and show that we were at 40 times what was expected from sevens. We ran some years more by doing a new technique that was binning, in the sense to improve the sensitivity at lower energy. And with all these results, we were able to set for the first time limits on the standard model extension. This was with light vector mediators. This was in 2020. We presented the Neutrino conference this year. And even we have not detected the seventh signal, we were able to place the world leading limit at the moment, since the threshold was very low, even much better than the Coherent that was detected some years before. So 4 years ago, in the second LASF4RI meeting, my colleague Irina presented the experiment, and in the perspective, she said that we were planning to install skipper CCDs, and the potential of those new sensors that allows us to reduce more the threshold detector has. And today, I'm very happy to show that we did what we planned, and 4 years later, I can show you the result that we had with those sensors. So we installed 2 sensors, skipper CCDs, very small mass, just to explore and to understand how we can measure, how we can download the threshold and control the background. The result of that was a paper of the performance, the data, the spectrum, and some constraints on light vector mediators and dark matter searches. And then in collaboration with the Atucha we studied the milli charged particles production in nuclear reactors. So this is our this year new results. So let me show how we improve the technique by using the skipper. So this is more or less the noise, the readout noise in 2 electrons that we have with a normal CCD that we were using, and now we are able to go to the sub electrons noise. So that means we can count electrons. I don't want to go in details, but we can. These are the spectrum for the low energy, so we can count electrons, and not only 1, 2 electrons, but we can count 100 or 2,000 electrons. So this, in this sense, this is a very nice sensor. I really love the skipper, sorry. For installing this, also we have to put new electronics, develop new adapted vacuum interface board that was developed in Brazil, and we reached for the first time this 0.15 electrons readout noise, and 5×10 to the -2 electron per pixel per day at the single electron rate. That is the minimum value that we can get in surface. With that, we were able to download our threshold, as I say, in 15 electron volts, and also to get a reduction on the background in 4 kilo DRU, where DRU is kilo event per kilogram per day per kilo electron volt. And here we have 2 plots comparing the 3 campaigns of CONNIE, let's say like that. This is the detection efficiency in function of the energy, and this is the background rate in function of the energy. And we can see that now we have the smaller mean value of the spectrum, and it's very flat. And keep in mind that the first bin is where we are interested. With this analysis, we create the reactor on -off, and we don't see any excess. For the moment, these sensors are very small. This encouraged us to go for a large mass sensor. But also with that, we will be able to put these limits on the light vector mediator, so we get something that is very compatible on what we had before, just a slightly better, but also we improve the models of the quenching factor. So it's the situation where we are now. And then also for the first time, we make a dark matter search for a strongly dark matter interaction in the Earth, where we can see we were looking for a modulation. We use a range of data where we were very, very low background and very stable among all the data set. And for that, we can place this limit. And as you can see, CONNIE is the blue one, and we are the best limited on surface. Of course, we cannot win to the dark matter dedicated events like Kemp that are also underground with a lot of background reduction. But we are very competitive, and this shows the potential of using skipper CCDs, this kind of experiment for these searches. As I say, CONNIE skipper data was showing with Atucha 2 data. You will learn more Atucha tomorrow So I have Dario will present a part of that tomorrow, so you will see the details of Atucha, but Atucha is also using a skipper sensor. So we show our data, and the idea is to study the milli-charged particles that can be produced in nuclear reactors. And then this particle can interact in our sense detector. So the interaction cross-section was recently calculated, and you can see that we have an increase in the range where CONNIE have its threshold due to a plasmon peak. So this put us in a very good situation, and this is the result that we is in archive, and we send to a physical review letter. So you can see in blue is Atucha, in red you have CONNIE, and the joint analysis is in dark, and with that we got the world-leading limits for this milli-charged particle. Also, we are using for the first time not only the primary gamma production, but also we add the secondary gammas, and you can see that we can improve a little the limits. And here you have the detectors or the data information about that we use for this analysis. So a lot of good things happening, but we need to go to more mass detector. So we already start to move on in the next step, that is to have more a sensor. But if we want to increase really mass, we need to find a new technology where we can do more compact modules. And this is what people from Fermilab were working, Fermilab and Argentina mainly were working a lot. And they developed this multi-chip module we call MCM, where we can sit 16 sensors in a single board. And this is much easier to handle in terms of installation and compact detectors, but also on the electronics, because we can control the 16 sensor with only one electronic board, what is really great, because before we were using one by CCD. So let me show, this was happened in CONNIE in May. So we installed this module that was produced, designed for school and produced by them. And so we are for the first time using these sensors as a proof of concept, installing in a real experiment. Then we have a prototype also in Fermilab. So we installed this in CONNIE. We have to change all our layout, and now we have a new VIB, and also we use a multiplexer board just to handle the 16 signals, and then the same electronic we were using before, just installed there. We are starting to take data, doing the performance study and optimizing just for starting to take data. We expect to be able to record background data in November, where the power plant will stop for a month. And the design that we did also will allow us to increase very fast and easily in mass, because we can fit more sensor as much as we want, just by putting one after the other. So we design in this way just to be able to increase in mass very easily. So this effort has a lot of synergy with Oscura, that is a dark matter experiment. But also we need to increase the flux, and so we start to discuss with electronuclear people about our needs, and now we found a position that is roughly at 15 meters of the core of the reactor. This will increase our flux by a factor of 4, but also since the position that you can see here in red, since the position is above all the building, also we estimate a reduction of flux of 4 times, what is really great because we need to reduce our background. So we are starting to design and to think in a very compact detector by using this MCM, but we need to change. We cannot put CONNIE in this position because it's a small space. So we need to optimize that. We are negotiating with people in ν-Angra just to have the permission to install something there. Because of that, yes, because of that, we did some studies of how much we need to wait until to reach the 7 sensitivity with the 90% confidence level. So if we keep the detector in the current position, 30 meters from the reactor core, we will need 200 days to measure sevens with the background that we had up to now. But if we move inside, you can see this was a zoom of the other plot. If we move inside, we will need to wait with the same background only 13 days. And if we are able to reduce the background by a factor of 4, as we estimate, it's only 4 days. So it's clear that we need to move on. This is taking into account 1 kilogram detector, what is really very challenging. Other challenge that we have to find is the quenching factor measure. Quenching is the efficiency of this recoil, because when the nucleus recoil, we have it can ionize. That is what we are measuring, but it has an efficiency that is roughly 10%. But in fact, we never measure below 3,000 eV, and as you can see, we are reaching 15 eV. In the CONNIE threshold. So some efforts are being planned in Latin America, Argentina, sites. This will be led by the Lambda. You will learn more about how great Lambda is tomorrow in the Darius talk. And also the Mexican group led by Sarkis, Josef Sarkis, that is a member of CONNIE, also is working on the theoretical quenching model. So this is all the effort that we are doing for the community. This is goes further than CONNIE Watucha. So just to finish, let me point it out, the synergy in the Latin America. So we have very collaborative efforts along the Latin America. So CONNIE is mostly formed by Latin America countries. We are several groups dividing the knowledge of the skipper CCD technology. Also, we profit of the support that we get from the HECAP with some visit from between Brazil and Argentina. Some institutions, people from institutions when changing. We receive in Argentina, we receive 2 persons from the university, the UFRJ, and then a person from Córdoba went also to CBPF and to the container for some installations work. So we are really very happy to have this possibility, and that helps us a lot to move on. And in one of these collaborations and work, when we got the milli charge limits that we present here. So this shows how this works well. Also, we work trying to get a more mass experiment, and we are working together. And also, I can say that we want and we expect to be the leaders of the new generation. So I think I don't have much time. So this is a summary and some concluding remarks. Let me just point out what I already said, that we need to move to a kilogram concept detector, and this will be done in synergy with all the works, all the groups that are working with the MCMs and with the SCURA collaboration that Argentina and Brazil also are members of that for the dark matter detection. And we think that we can keep this leadership of neutrino detector by using skipper CCDs in the South America. So thank you very much.
Okay, thanks, Carla. Are there any questions from Zoom first? Or in the audience here?
I have a question. So Carla, congratulations for this amazing work of the CONNIE collaboration. It's really nice to see how much development you have made in this since the first strategy. So this is amazing. So my question is, okay, the long term, so you're going to keep growing, and the idea is to go to a kilogram mass detector, and how much in the future you think that will happen?
How, sorry?
How how long in the future this kilogram mass?
Okay. Well, now that we install this MCM, we need to make the sensors work. So this is going to be roughly 1 year if you want. And then we will in parallel work on building this new experiment to go nearby. And then all the efforts of having this MCM, the MCMs are working perfectly. I did not show some data, but we were testing this sensor before being to Brazil. And we have the initial tools to do all this analysis. And then we are now, but because it goes in synergy with Oscura. And in Oscura, we have a setup of 16 MCMs that we are running and we are analyzing, and then these 16 MCMs will be put all together in the super module. This will happen until the end of this year. And once in 2025, we will have running these technologies in a stable way in Oscura. I think that we can start to think to put this module in CONNIE with Natucha, in ν-Angra with Natucha, in any of or in both, if possible. So person power is always a problem. So I would say a couple of years starting to move. When we will set up this super module that is 16 MCMs, is 130 grams detectors. And then we don't need to go really to a kilo if we move inside the power plant. So maybe 2 or 3 of those super modules will be enough. And this is something that is rather easy to do with the technology that we already have. So I use 1 kilo because it's easy to make the calculus, and also because it's an order of magnitude.
So just a follow-up. So imagine the bottleneck is actually this skipper CCD production. So where are they being made?
The CCD is Fermila. All the production is Fermila, so they do the the MCM and also the super module.
Thank you.
You're welcome.
Any other question from outside? If not, let's thank Carla.
Thank you.
And our next contributor is Ricardo Gomes. He's going to tell us about NOVA. Ricardo, yeah, we can see your slides. You have 20 minutes. Thanks so much.
Okay. Can you confirm if you're listening to me well?
Yes, we
Okay.
can hear you and see your slides.
Okay,
Yep.
good. Great.
Okay.
So thanks for the opportunity for talking about NOVA. Unfortunately, I could not be with you in person, but I'm gonna talk about the Latin American contributions to the NOVA experiment. Sorry. I'm Ricardo from the Federal University of Goiás in Brazil, and the other 2 groups from NOVA, from Latin America on NOVA, are the Atlântico and Magdalena universities. So the outline of this presentation is I'm going to briefly talk about the NOVA and then the Latin America contributions on commissioning, maintenance, running, Monte Carlo simulation and production, and the analysis both in neutrino and cosmic rays. So the NOVA collaboration is about 200 collaborators and 48 institutions. From Latin America, you have the Goiás, Universidade del Atlântico, and Universidade del Magdalena, both in Colombia. So this is a not very recent photo from the Fermilab site, but you can see here the LINAC, the booster, the main injector, the retired Tevatron. Here is the antiproton source, and here you see the NUMI beamline going into the near and far detector, the location of the near detector of both MINUS and NOVA, the location. It was not built yet. And so that direction is pointing to the north of Minnesota. You see here MINUS, NOVA a little bit off axis, just for comparison, the DUNE beamline here as well. So this is the near and far detector of nova. Near detector is underground, far detector is on surface. And this diagram here shows the composition of the beam. You see that first it is almost entirely mu neutrino. Then we measure the appearance of nu E appearance, and the nu mu disappearance, converted to nu tau and nu E, obviously. So this is the nu me. We have two horns, magnetic horns, focusing positive or negative hadrons and producing neutrino or antineutrino beam, just changing the current. And here I'm showing the on-axis spectrum in case, I mean, this was the spectrum that we observed in minus plus. And we chose for nova the 14 millirad angle. This it shows that it is a narrow spectrum on 2 GeV peak energy. And this is very good because it is on the maximum for the nu E appearance and in the minimum on the disappearance probability. And here you can see the composition. This is in log scale, so it is almost entirely nu mu, a very small contamination of nu mu bar and nu E bar. I mean, for the what we call FHC, forward horn current, which aims to produce a neutrino beam. The nova detectors are made of PVC cell, a PVC cell filled with mineral oil, which is the scintillator. And we have the optical fiber connected to APD, avalanche photodiode. So you have a plane of vertical and another one horizontal oriented cells, and alternating vertical and horizontal. This is the to have an idea about the scale of both detectors. The near detectors, concerning the electronics, the near detector has 20,000 channels, and the far detector 344 channels, more than 99% operational. And the topologies that we observe on nova are these ones, the nu mu and nu E charged current, and the neutral current as well. So here you see top view. This is the Z direction. This is X and Y. So you have this the top view and the side view of the detector. This is far detector, 550 microseconds without window. And there are, since it is on surface, there are a lot of backgrounds. And you can see here a neutrino event from the beam. After background reduction and after synchronizing the time with the nu me, with the accelerator, we get this 10 microsecond window. So this is a time zoom. Then you see the interaction. So the nu me beam is recently approaching the 1 megawatt power. So since minus, it was 100, 200, 300 kilowatts. Recently, it was 600 on nova. And typically, it was 900. And now we are reaching 1 megawatt. So we are now in a 10 years of data taken. And most of the analysis that you are already familiar were based on this 2020 data set, including the joint nova plus T2K analysis. Now we are just publishing and presenting the still preliminary results based on this 2024 data set, which included almost 100% more neutrino beam. So orange, sorry, orange is neutrino and blue antineutrino. This is the neutrino oscillation framework. Obviously, we are interested in contributing to these three main questions concerning the θ2-3 octant, which is related to the composition of the nu3 in terms of nu and nu tau, the neutrino mass ordering, and the CP violation in the leptonic sector. But also, we do on NOVA beyond standard model physics, for instance, sterile neutrinos, non-standard interactions, and now neutrino decay, just for examples. Also, very important measurements on cross-section measurements, cosmic ray physics, supernova, multi-messenger astronomy, and many other topics. So concerning the oscillation, neutrino oscillation framework, this is very well known already. This was our result from 2020, based on our 2020 data set. And you can see that our allowed region here in black solid is very competitive on delta m squared and sine squared of θ2-3. And concerning delta CP versus sine squared of θ2-3, normal ordering and inverted ordering, we are also very competitive on that. You can see as well here the T2K measurement. In the inverted ordering, we agree, we favor the same region in terms of delta CP, but on normal ordering, we favor different regions. Here you see the T2K region, and here in blue, our NOVA 1. So there is a tension. There is a very interesting tension on that. These are the same plots, but based on the 2024 data set. You can see here that we improved a lot our allowed region on delta m squared and sine squared of θ2-3, which is this blue one. The joint NOVA 2020 plus T2K is here in blue as well. This line, dashed blue, and the T2K1 is red. Here you can see that we improved from the light to dark blue, from the 2020 to 24, but we still have this agreement on the inverted hierarchy, inverted ordering, and we disagree. There is still a tension for the normal ordering. That motivated us to do this joint analysis with T2K, and we will have more results soon. So now, instead of continue talking about the results of NOVA as a whole, let me focus on the Latin America contribution. For instance, on commissioning in the near detector, we contributed to the APD, the Avalanche Photodiode Quality Assessment Task Force, testing all the electronics and the APD and doing the maintenance of all of them in the near detector. Also, this work included training new people and helping with documentation. Stefano, which was my PhD student, was one of the on-call emergency contacts for fixing problems underground during about 6 months. We set up a remote operations center at Goiás. These are the locations of the NOVA rocks around the world, and we do have one here in Goiás, which is fully operational since March 2016. We had already some expertise on this kind of operation since 2011, I guess, on minus, then minus plus, and on 16, we concluded with the hardware and set up to do this for NOVA as well. So this, of course, in addition to the collaborators here in Goiás, possible users are the Universidade de Atlântico and Magdalena, and also other NOVA collaborators. For instance, a couple of times NOVA visitors here used our NOVA rock to do shifts. We are going to do the data taking up to 2027, so 3 more years. And of course, it is being used for shifts, for backup. For instance, if someone has for some reason a problem during the shifts, we are being contacted to cover the shifts. We do also training new collaborators in our ROC, and it is being used for public visitation as well. Concerning production, I mean, the conversion of raw to reconstructed data in Monte Carlo using the grid, this is a very important service for the collaboration, and we used to be one of the responsibles for the production. This is not up to date, but a postdoc here in Goiás, Tapazi Ghosh, was serving as a production shifter. And Enrique, which was a student, then postdoc on NOVA, he was also working on the production team, and he is now a professor at Madalena University. Andrea Barros, from a PhD student from Mario, she's been trained to be a shifter on the production group, and soon she will contribute to that as well. On simulation, my student, Stefano, contributed. I mean, this was one of his contribution to NOVA. He integrated the Corsica, which is a cosmic ray simulator, to the NOVA ART framework as an alternative to a previous simulator, with the advantage of the Corsica being a complete simulation of the shower, and the CRI was not doing that. And this was used and is being used for many different studies on the exotics group. I mean, the group that used to investigate cosmic ray physics, supernova, etc. For instance, it is being used for seasonal variation, multiple muons, east-west effect, and many other. And there is, I mean, there was this potential use for DUNE, but because it is being done in DUNE as well. This integration of Corsica to the framework of DUNE. Concerning analysis, our group with Tapazi, she was responsible to do the estimation of the tau neutrino background for the first muon neutrino disappearance. I mean, the oscillation measurement, the investigation of the contamination of tau neutrino was done by our group, which is reported here in this paper. Here you can see the unoscillated prediction, the number of events. So it is a huge effect of constructing an experiment on the minimum of the probability is great, because you can see this difference between the unoscillated and the oscillated, I mean, and the data. And here you can see all the backgrounds summed, including the one that we estimated. Concerning the exotics group, I mean, the studies of cosmic rays, we proposed and we were responsible for all the analysis of the seasonal variation using multiple muons in NOVA near detector. Then all we did was used to repeat the analysis, but now on the far detector. Concerning cross-section measurements, Tapazi was responsible for the investigation of this channel, the nu plus pions at the near detector, and the Magdalena group, the Henrique group, is very active on many analyses, contributing to the most recent measurements from NOVA on different channels, inclusive, exclusive channels for these cross-section measurements. On the NUCS group, which takes care of steriles, neutrino decay, and other analysis like this, involving neutrinos. Mario Acero is one of the conveners, and his group and my group was investigating the NSI, non-standard interactions, my student was responsible. He was doing the master dissertation under my supervision, and now he is doing his PhD in Mississippi, still on NOVA, still on this analysis. And we can see this is preliminary. We just submitted this paper, and we can see the sensitivity that I have been shown to you about delta CP and sine square of theta 2,3, but including some parameters, you lose sensitivity on those standard oscillation parameters. And so it is important. And we, in addition to do the investigation of the effect of this kind of parameters on the standard oscillation parameters, we also constrained a lot this kind of parameters. Concerning current analysis now that both the Atlântico and Goiás groups are working together, is related to the sensitivity analysis on neutrino decay. Andrea Barros is Mario's student, and Danielle also is my student, and they are studying the possibility of including this term in the Hamiltonian, which takes care of the decay. So first, we are considering just the decay of the nu3, I mean the third neutrino, and considering a certain value of this parameter, we can see the effect of the decay on the disappearance and on the appearance probability.
2 minutes, Ricardo.
Okay, I'm going to conclude now. So as a summary, the Latin America is contributing significantly to NOVA, not only to NOVA, but to the neutrino experiments in general. These three groups are also working on DUNE, and we are contributing on instrumentation, on running shifts, the rock, on simulation and production, on analysis, including coordinating, proposing new topics and leading analysis, for instance, on seasonal variations, cross-section measurements, NSI, neutrino decay, and we are strengthening our Latin America collaboration, for instance, on these two analyses, NSI and neutrino decay, working together and looking for opportunities to foster our partnership. For instance, visiting programs in Latin America and to allow visits to FrameLab as well. So I want to mention the support from CNPq and FAPEG, which is our funding agency here in Goiás. And that's it.
Thanks, Ricardo. Are there questions for NOVA related?
So Ricardo, again, congratulations for this very nice work. So I have a question about the background that you showed in one of the first slides, some signatures of neutrino interactions in NOVA, and you have to clean the background. My question is, what is the main background for that?
Okay, yeah. So one interesting thing here is that we are using now a convolutional neural network, a visual neural network, and here in the far detector, the main background are the cosmic rays, because this is on a surface.
Right.
So only with the synchronization of time with the beamline, with the accelerator, we can do a time window, which is this 10 microsecond window, and removes a lot of background. So this is the most important.
So you don't have veto on top of the detector, for instance. Sorry? You don't have a veto, something to veto cosmic rays in the top.
Yeah, but it is not significant. There is a small veto, but it's not significant. So for Minos, there was a mine underground that we could build the far detector. To build this with these 810 kilometers in north of Minnesota. There was no mine that we could use. So the idea was to use to construct to build the FAR detector on surface and use our capacity to process computing the background elimination.
Thank you.
And we succeed on that.
Very good. Thanks.
I have a question also regarding your setup for a remote control room or shift taking place. So is this place just for monitoring, or do you have some sort of that data acquisition superpowers that you can exercise? What is the level of engagement of this setup?
Okay. Let me share again here. I changed the. Okay, so this is not only monitoring. This is a very important issue. We control totally both detectors and monitor the beam line. So this is not related to our. I mean, this is our part of our responsibility on the data taken process. But the data taken is 24 hours per day during all time. Even now that the beam, the accelerator is not working, we continue taking data, mainly thinking on supernovas, but also on atmospheric neutrinos and the cosmic ray physics. So we control the experiment and monitor.
Okay. Thanks. Any other question from outside or here? If not, let's thank Ricardo again.
Okay, thank you.
I don't think Carlos, who was our next speaker, is showing up unless Carlos, you're maybe hidden there somewhere. So we're gonna break for a little bit.
There are messages in the chat.
Their messages in the chat.
Okay.
Okay. I just saw that it seems to be hidden by.
We have next Deywis Moreno. He's gonna tell us about the Colombian contributions to DUNE. So Deywis, the virtual floor is yours. You have 20 minutes, and I will warn you before 2. Okay.
Okay, great. Thank you. Thank you very much for, can you hear me well?
Yes, we
Okay.
can.
Okay, so thank you very much for the organization of this symposium. I think it's very important, the continuity on this initiative. I apologize for not being there to give this talk in person as originally planned. So as you mentioned, so I am going to give an update on the activities of Colombian institutions in the DUNE experiment. So I'm going to give an update related with the past update on 2020. So here you can see a list of the current institutions involved on the DUNE experiment. Since the last update, 3 new universities have joined the collaboration. The Universidad of Medellin by the end of 2020, Universidad of Antioquia in 2022, and Universidad of Magdalena in 2023.
I don't see. You're not sharing your screen.
No?
No, he's sharing the screen. No?
Can,
He's sharing.
Oh, maybe we're not sharing from here.
Oh, maybe we're not sharing from here. Okay.
I can see the screen.
No, I think so.
can you see?
Maybe.
Can you see the slides?
Sure. I didn't do anything.
Claudio, can you see the screen or not?
No, I don't see any slides. No.
So try to. Are you on the cell phone or what?
No, I am in my computer. I will stop sharing.
No.
Okay, I will I will reconnect, okay?
No, 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 it should be another. Try to change the setting that you're looking at.
Now I can see it.
Now
Now,
you can, right? Okay,
Now I can see it.
so now it's good.
Yes.
Okay, sorry for that. Well, yes, as I was saying, so since the last update, so 3 new universities have joined the collaboration, and most of all the institutions are already making some concrete work on the experiment. The main focus are the instrumentation for the 2 far detectors modules. In particular, we are working on the development of the electronics for the photon detection system. I am going to give more details in a few moments. The activities are also evolving into other systems. For example, we are also institutions starting to work on the calibration for the photon detection system, and other institutions starting also to work or thinking to contribute to the NIA detector, that is other of the big important detectors of DUNE. So yes, so the DUNE experiment is the deep underground neutrino experiment. I am not going to give many details about the experiment, because on Monday, I think it was a very nice presentation by Leah related with the characteristics of the experiment and the scope of this experiment. I just want to remark that the 2 technologies for the main, for the first 2 far detector modules are already defined. It consists of ATPC filled with argon in liquid state. Actually, 2 configurations are defined, one called the horizontal drift and the second one named as vertical drift. In the first case, the electrons are going to travel in the horizontal plane, and in the vertical drift, the electrons are going to move in the vertical direction. In both systems, we are going to have a photon detection system that is responsible for detecting the photons that are produced by the argon ionization. I would like to remark that in both cases, the photon detection system has as a base the Arapuca concept that you already know. Is a brilliant idea developed by Ettore and Anna in Brazil. And around of this technology, I would like to mention that all the Colombian and in general Latin American participation is centered. For that reason, it's very, very important, this contribution. As I mentioned, we are working on the, maybe it's much better here. So as I say, we are involved on the so-called warm without electronics for the DUNE photon detection system. This is known as DAFNE, detector electronics for acquiring photons for neutrinos. This board is the board responsible for the digitalization of the signals coming from the Arapucas, the silicon PMs that are part of the Arapucas, and the signals are bringing outside, and the DAFNE board is taking that signals, the analog signals, make the digitalization, and also sending the data to the data acquisition system. For that reason, it's a very, very important part of the photon detection system. This board was originally developed as a collaboration between, it's still a collaboration between Fermilab and Latin America. So the design started with the travel of the visit of Professor Javier Castaño from Colombia and Juan Vega from Peru to Fermilab. So for that reason, I think this is very important, this announcement that was done the past Monday about the possibility to reactivate this kind of visits between Fermilab and other countries. That because it is very important for the doing this collaboration more strong. Well, so this is, as I mentioned, something that happened around 2019. So by 2020, so after the past update in this symposium, in the second version of the symposium, so the Daphne board work of development progress in a very good way. Here you can see, for example, the schematics that has been finalized and reviewed by the end of 2020. And also you can see on the right side some general scheme of the Daphne interfaces, and at the bottom and the right bottom part you can see also the initial Daphne board with the parts already placed there. I mean, an image of what is expected to be the board at that time. At the beginning of 2021, so the first boards were produced. Actually, the PCB was produced. That was produced at Fermilab, and also some initial tests were performed on the boards. After that, so the first 10 prototypes boards were produced also in the area close to Chicago, and the first physical boards or prototypes were ready by September 2021. So you can see a picture of the first version of the Daphne board on the chassis. So additional tests were performed. So in general, the assembly process was successful. Only one ADC was not working properly, and some different checks were performed on the board when minor details or minor issues were found, and that was all the information was collected for the next iteration of Daphne. But from this board, the main hardware blocks have been validated. The same year, 2021, some of the boards arrived to Colombia. So we were also involved, not only in the design, but also in the test of the boards. So you can see here, for example, one of the tests that has been performed on the boards, especially on the digitalization of the signals. And we were testing the digital part of the board. Meanwhile, so some of the minor changes that were found, or errors that were found on the layout of the Daphne 1 were implemented and corrected, and a new version of the board called Daphne V2A was also produced. And in this case, also the analog part was tested with help of our colleagues in Italy by April 2022. So the last year of this year, so we were able to test the boards on CERN. As probably you know, there are two prototypes of DUNE installed at the Neutrino platform at CERN. The left image is presenting very, very famous of the inside of one of the cryostats of the DUNE prototypes and DUNE prototypes at CERN. And at the right of that picture, you can see me installing some of the boards on the top of in rack on the top of the one of the prototypes at CERN. So since then, that was the installation. This year, the protodunes were filled out with liquid argon, and we start to take in data. So on the bottom, you can see some image of some noise, initial noise that we catch at the beginning of the test. But right now we are having very, very nice data taken with the Daphne boards. And of course, this is going to be presented in the next collaboration meeting that is going to happen in 2 weeks in Santa Fe in the US. But in addition to that, the Colombian groups are still contributing with some firmware and software for the boards. In particular, the Universidad AIA is working on the development of a robust self-triggered algorithms that will be implemented on the boards and will be the base for the data taking in the coming months. And we hope for the far detector horizontal drift. And also, Universidad of Antioquia is working on a Daphne test bench board that can help us to make a quick testing of all the capabilities of the board. That's something that is going to be required when the boards will be produced and then installed in South Dakota. You can see on the bottom right some initial concept design of this test bench. I would like also to highlight that this is also a joint work with our colleagues of Mexico, in particular Omar and Luis for Singestar. But well, not only right now, the Colombian institutions are not working only on Daphne. So the scope of collaboration is quite extended to other instrumentation inside of the PDS, but also to other systems. In particular, Universidad de Medellín is working closely with the South Dakota School of Mines and Technology in the calibration and monitoring system for the PDS system of DUNE. And also they are planning to work on quality assurance, quality control on of some of the fibers that are going to be used for this calibration. And also there is some novel concept that is going to be used for the vertical drift that is called power over fiber technology. That is basically the transmission of signals and power for the silicon PMs using fibers. So this is something that is going to be used for the vertical drift, and Universidad of Medellín is working on this and is planning to contribute in that area. Universidad del Atlántico is also planning to collaborate with one of the detectors that is going to be part of the first for the phase 1 of the near detector. That is all detector that is going to be built close to Fermilab in order to make some initial measurements of the neutrino beam. Very important also for the complete physics program of DUNE. And in that case, Universidad del Atlántico is planning to work with other institutions in the calibration system for the muon spectrometer. In addition to this, of course, this work on instrumentation, I would like to mention that Universidad de Medellín, for example, is involved also on the Beyond Standard Model physics group of DUNE. They are making very nice contributions. So different areas related with these searches of physics beyond standard model, and also other collaborators are working in searches of dark matter, searches at DUNE or trigen signatures. I mean, there are, in addition to this work, so many groups starting to work on different aspects of the analysis, and also thinking in data analysis. Well, so just to remark, so some remarks. So I always like to show this picture that you are seeing here. Here you can see the countries that are already part of the DUNE experiment, and in particular you can see that the Latin America role on the experiment is center of focus around the photon detection system. As you can see that many countries are working, for example, on the DAFNE design, mainly Colombian institutions, as I mentioned, but I would like to remark that also Peru is involved on the software part of the DAFNE board. And also in the past, we have Paraguay also helping us on the initial design of the DAFNE board. The first bullet of this slide is taken for the previous presentation. Because we are still thinking that the participation in DUNE is an opportunity that we already have. We would like to continue making a continuous progress on this experiment. We are right now changing from the design phase to the production phase. In the future, we are going to have also the installation phase of the experiment, and then we are going to have the data. So I think there are so many years ahead where we can still contributing to the experiment in different areas and making an important role in the experiment. After the last update in this LASF4 infrastructures, this is the second one. So I think many good things happen in addition to what you already mentioned. So I showed that the DAFNE boards are already designed, tested at taking data. So we are expecting to have a third version of DAFNE, where we are going to change one of the current digital systems. In particular, we are right now having a architecture that is FPGA plus microcontroller. Now we are going to have a system-on-chip system that is only one chip that involved where you can have, I like to say, the microcontroller embedded in the chip. So in addition to that, I would like to mention that one patent was granted in Colombia based on the knowledge that we got. We also started to make a network of universities and local electronics manufacturers. So the idea of this network is join academy and industry toward the goal of produce boards or produce some of the electronics here in Colombia. So also some former DAFNE developers from Paraguay are right now doing the PhD or already finished the PhD in Europe. One of the Colombian PhD students at that moment is right now postdoc also in Italy, working still in DUNE, in DAFNE. And also I would like to mention that we make the One of the DUNE collaboration meetings was held here in Colombia, in Santa Marta. It was the first time that one of the collaboration meetings was not happened in Europe or in the US. What I think is very important to show that the role that Colombia is playing in this experiment is recognized for the collaboration. And this is something that is happening right now. We are other countries planning to hold the future collaboration meeting, so making some kind of decentralization of these events. And well, just to finalize, this is a slide that I presented also the last time. So here where you can find some recommendations that at that moment we thought that where we need to follow in order to make this initiative and also this collaboration go forward. I think most of these points we already achieved. For example, increase the transfer of science knowledge. As I mentioned, we have this patent granted here in Colombia. The communication between research and industry with this network of universities and electronics vendors here in Colombia. But of course, there are other many points that still need to be lot and hard work. For example, try to make the research and innovation policy be on the political agenda of our government. That is something that we need to urgently start to concrete. Well, thank you very much. And this is everything that I have to say. You have any comment, question?
Thank you. Okay, so we have time for quick questions. Maybe from outside or from here. So just very quick question. You mentioned about the renewal of these programs at Fermilab. Does that mean that the access to the lab gotten easier this recently, or what is your experience?
Well, so what I mean is in the past, for example, we have this very nice scholarship that was something that allows, for example, Javier to travel to CERN. Also, my PhD students have the opportunity to apply to that scholarship to travel from Colombia and stay at CERN, at the Fermilab. So this is something that honestly, I didn't see again. I mean, I didn't see a call like that. So the announcement that was made on Monday that this is going to happen again. So it is very good in that sense. I know that, I mean, I know there are some issues for some I mean, to allow the visit to Fermilab, but that is something that actually didn't happen with us. This is only in terms of resources, more, I mean, funding. That is something that I think is important. But for the rest, I think this, for us, is there was any problem or they were any problem related to that.
Okay.
Just a comment about that. So LAA HECAP is talking to Fermilab, trying to push this program. We had 1 or 2 meetings, and we're still waiting for Fermilab to come up with a proposal.
Yeah,
I hope this happens. No? But, we'll see.
I think it would be great, and maybe sorry. Other thing that it will be good also try to with this initiative is try to see the way of having a more close contact in order to see how the agreements between countries can be design it. So we have an experience when we try to have an agreement between Fermilab and Colombia in order to have some access to resources from Colombia, but there are some kind of political issues, or it was not very clear if we can do that directly, or if this is something that need to be done between our Ministry of Science and Technology. I mean, there are so many details that I think this is if you are in close contact with Fermilab, this is something that can help us to try to have this kind of agreements for future, collaboration or a closer collaboration between Fermilab and Colombia, for example, or between Colombia and Peru. I think this is something that usually happens. It's not clear the proceeds in order to do that.
Okay, let's thank Deywis again. Next, we have Ernesto Kemp, and he's gonna talk about the ν-Angra experiment.
Ernesto is here.
Oh.
Ernesto,
Very nice to see
he
you.
drove all the way from Campinas.
Very good.
This is the
Yeah.
pointer.
Well, the pointer actually.
Don't have laser because of.
Yes.
Okay. Use the hands, no problem. So hello, good afternoon to everyone. I will talk, so we are in a symposium talking about large infrastructures and big experiments of the big science. And I will talk about a small experiment, but nevertheless, producing very nice results. And we are creating a facility inside the nuclear power plant in Brazil that it's cheap, and we are producing very nice results in particle physics. So let me first make a preamble about the reactor neutrinos as a safeguards tool. So this is a picture showing the distribution of 440 nuclear reactors all around the world that produces this large amount of plutonium. And even the diversion of a small amount of this spent fuel is a big concern for the International Atomic Energy Agency. So it's necessary in this case to develop new tools to increase the safety of the safeguards that measurements that the agency already had. So to monitor nuclear reactors with anti-neutrinos is not a new idea. You remember that the discovery of the neutrinos were made to use neutrinos from nuclear reactors in the 50s. So in the left plot, it's a time evolution of the counting rate from an experiment that ran in San Onofre in California, in the USA, almost 15 years ago. And it's possible to see the decrease while the reactor was closing to the outage for refueling. So a big decrease in the counting rate, and then another increase when the reactor was turned on again. And another interesting result came from the 80s with the people that operate a detector in nuclear power plant in Hovin in Ukraine. And they had this beautiful plot showing the correlation between the counting rates and the thermal power delivered by the reactor. So these are the main ideas to use and to build experiment in the Angra dos Reis power plant. So our collaboration is made from faculty and students from different institutions, 6 different Brazilian institutions in Bahia, Rio, Minas Gerais, São Paulo, and Paraná states. This is a picture of our experimental lab. So we are here, very close to the concrete dome for reactor containment. And this is a picture of the lab. We are operating in a refurbished container long 12 meters. and we are housing two different experiments, ν-Angra and CONNIE, which was described by Carla in a previous talk. So this is our neutrino lab, okay? The major objectives of our collaboration is to develop these methods for non-invasive monitoring of reactor activity, mainly related to the creation of new technologies for safeguards and non-proliferation efforts, of course, in coordination with the International Atomic Energy Agency. And as a byproduct, we are creating expertise in all the phases of an experiment, since the design, prototyping, construction, operation, data analysis, and results, okay? So as I said to you, in 2008, the agency published this document, and the guidelines at the time was recommendations to develop detectors that could be built and operate in a very simple and small infrastructure, just like a container, and moreover, to operate at surface that is very challenging. All of the previous results that I've shown to you were produced with experiments that was installed in caverns or in rooms that it's underneath the surface, okay? So very with a overburden enough to reduce the background from the environment. So this is the principle of our detector. Our detector is made by different nested volumes, just like a Matryoshka doll. And at the center, we have a tank filled with water, doped with 0.2% of gadolinium in mass. And this is where we are taking data from the antineutrinos coming from the reactor that produces the inverse beta decay reaction that it's showing in the upper part of the draw of the reaction. And in the IBD, we expected two different products, the positron and the neutron. The positron, it's produced almost simultaneously with the interaction of the antineutrino, and it releases energy, a flash of Cherenkov light. And then after thermalization, the neutron is captured by the gadolinium atoms and release gammas from the excitation, which sum up to 8 MeV. So it's a very precise energy, and this should happen in a time interval with the time constant of 12 microseconds, and I will describe to you later. So the outer volumes of the detector, it's for shielding purpose, and also they work as active vessels because there are some PMTs inside the external tanks. This is a picture of the electronics. So the data acquisition system of our experiment can be divided in the trigger system, which is based in a simple Raspberry Pi, which has a very flexible configuration. And then the trigger, it's sent to the front-end electronics that is responsible for discrimination, amplification, and shaping of the signals of the waveforms of the PMTs that then are sent to the digitizers. And the digitizers, it's responsible for making the integration of the charge and to measure energy and time in between events. And then we have a system, the network system, that controls the flow of data that is produced in the lab and then goes to the CBPF. And then we have another mirror at UNICAMP. We also have tools to monitor the experiment outside based on a dashboard that we can control the activity of the detector anywhere in the world, even here if you want. And so all of these were designed, produced, and built and assembled in the detector in Brazil by the engineers and the physicists of our collaboration. These are some pictures of the detector commissioning, the people making the clean installation of the PMTs inside the target, and then after the assembling of the different volumes, we have this picture showing the whole tank being transported inside the container. And finally, in this picture, we show the electronics, and behind it, that yellow blanket, it's covering the big tank of the external tank of the detector. To the operations, we are able to equalize the gain of the PMTs at the level of single photoelectron. So since we know the position of the peak of the single photoelectron as a function of the high voltage applied on the PMT, we can equalize the gain of the different, or the 40 PMTs of the experiment, and to align all of them to grant the uniformity of the detection. And the stability, we can check here the trigger rate of the experiment, that it's very stable, and it's a key point for the analysis that I will show to you afterwards. Another stability check can be done by check the Michel electrons. So muons decay inside the detector, we can observe the electrons of the decay, and at the left you can see the remarkable agreement in between the data that were collected with Michel electrons and the Monte Carlo of our experiment. So the stability of the experiment can be checked in an unbiased way in a physics phenomenon that is not related to the reactor, to the neutrinos from the reactor. It's Michel electrons are produced every time inside the detector. So by measuring the amplitude, the position of the peak, and the width of the Michel electron spectrum, and following these parameters along the time, we can make we can check the stability of the operations. So let me describe to you the analysis. Most of what we will describe to you is in this paper that we published in last June. And if you're interested in some details, you can check there. So as I said to you, we are looking for ICD events, and the strategy is to correlate 3 different quantities. One of them is the time interval in between the detection of the positron and the neutron. Another one is the expected energy of the positrons, that it's the prompt event, because it's correlated, it's totally related to the spectrum of the antineutrinos produced inside the reactor. And then the neutron energy, that is the delay pulse, as I said to you, it's gammas with no energy from the gadolinium, the excitation. And so we can check where this energy of the second pulse can be looked for. So this is a plot with the time interval in between two consecutive events in the ν-Angra experiment. And there are 3 main components. There are Poissonian processes that can be described by 3 different exponentials. There are the muon decay, the neutron capture, and the background noise. So we made a fit that we could totally free the parameters of these exponentials, and we got from the muon decay 1.9 microseconds, that is very good, and the neutron capture almost 12 microseconds. And we were expecting 15 because during the designing phase, we decided to use those that 0.2% of gadolinium to have 15 microseconds of delay, and we got 12 from the data analysis. And then the background noise is almost flat as expected for uncorrelated and random events. And we cannot make calibrations using radiative source inside the power plant. So we have to make our calibration totally based on Monte Carlo. So we used a very detailed GNT4 simulation of the detector, in which we can shoot positrons with the expected energy, came from the IBD interactions, and then knowing the energy in the simulation, we can check the photoelectron counting in the PMT, so we have this very nice linear relationship. And this enables us to build the interval of energy of the positrons to looking into the data to select the first pulse inside this energy range, okay? That PDF was based on a simulation from energies of the antineutrinos that it's converted to positrons and then shoot it inside the detector. And we can do the same for the neutrons. So these are the results for the energy of the gammas released by neutron captures inside the detector. And at the same way, we build the PDF functions and then selected the interval to looking for the energy of the second pulse in the pairs. So based on this strategy, we selected events in the data set of our experiment, and I make the non-off analysis that it's simply to check, to compare the data when the reactor is on and when the reactor is off for maintenance and refueling. This happens once a year. Okay, so these are the results. These two plots show the on-off analysis in two different time periods, and the upper part of the plots are the spectrum of the positrons in the on situation, that is blue, and off, that is the yellow, and in the bottom part, there is the subtraction, okay? We can see a clear excess in the energy range of the positrons expected from the IBDs, and doing a hypothesis test based on chi-square as a null hypothesis that the excess is only due to fluctuations, statistical fluctuations of the background. We rejected the null hypothesis with a p-value that it's less than 10 to the minus 9. It's a very strong signal. So how much time do I have?
5 more minutes.
Okay. So after let's say to show that we are able to monitor the reactor state, some possible upgrades are to install segmented scintillators on the top and the bottom of the tank to help us to understand the background, because it's possible to identify muons and then separate them from the environmental background. Another possibility is to start some enhanced calibration methods with more sophisticated simulation models, and who knows, perhaps to use some radioactive sources, and also using LEDs with different wavelengths to check the gain of the PMTs. Another idea is to improve the DAC using artificial intelligence in FPGAs to select the trigger, to make the triggers not based on the thresholds. So this increases the efficiency for post selections for the IBD pairs. And another possibility is to replace the water with a water-based liquid scintillator. That it's well known right now. Everyone knows. There are articles published about that, but okay, it's not so okay. But it's possible, it's feasible to use to replace the water right now for water-based liquid scintillator, okay? And I will talk very quick about the ν-Angra 2.0, that it's in a scenario for, let's say, 5 years from now, that it's to use the low temperature calorimeters to detect sense current scattering Neutrino-Nucleus. Is the same physics of the CONNIE, but with different technology. And but the principle is we have crystal under very low temperature, millikelvin temperature, and so energy depositions of the interactions can be translated into phonons, And this increases the temperature of the crystal that it's detected by very sensitive sensors. And so more on this on the talk of my colleague Pedro Guillemot from USP that will describe the efforts and the strategy to build a laboratory of cryogenic calorimeters here in Brazil. So lower the temperature, our sensitivity to energy deposition is better, okay? And so a millikelvin particle, at millikelvin temperature, a particle of a kilo electron volts produces an increase in temperature in the order of micron electron volt that can be detected using quantum sensors that I will talk about in a few minutes. So the challenge, the technology is well known and used by different renowned collaborations studying neutrino-less double beta decay, dark matter, and coherent scattering neutrino-nucleus in different underground laboratories around the world. And the current typical dimensions is a 5 by 5 by 3 cubic meters. So it's challenge, but feasible to squeeze this detector and to fit it inside our lab in ν-Angra, okay? So this, we change our detection technique from Cherenkov to SENS. It's a different technique from CONNIE, but we can explore the complementarity in between them. And it's interesting to, I have to emphasize to you that the development of this kind of sensors, the transition edge sensors and the kinetic inductance sensors to monitor the temperature of the variations in the temperature of the crystal, it's quantum sensors that it's almost the new holy grail for the next generation of qubits, that it's the same technology for qubits. And also we can extend the physics program from anti-neutrino applied physics also to study fundamental physics, because changing the material of the cryo detector, we can study the behavior of the cross-section that it's material dependent, okay? So just to be, I will move very fast on this. So basically, this can be found on internet, okay, on archive. So basically, in the next 5 years, we are planning to make those upgrades that I described to you in the water tank, and after 5 years, and during, in parallel, develop the cryogenic sensor, and then after 5 years, possibly, we can start the operations. This is the estimated cost of this whole phase. It's around $1 million. And as a conclusions, we have the ν-Angra neutrinos. The neutrinos-ν-Angra experiment was totally made in Brazil by scientists and engineers here. We have designed, prototype, built, test, commissioning the detector, front-end electronics and DAQ boards, and we have very nice results on that. We have showing that we are able to make the data taking a very stable and in a good way, in a very affordable way. So different technologies can be explored in the future by the detectors, such as the water-based liquid scintillator that can open doors for additional physics stops of the experiment. And we can go towards new technologies as the cryogenic calorimeters in partnership with our new colleague, Pedro Guillemot, that will talk about that tomorrow. Final remarks. ν-Angra and CONNIE has established a very, very nice facility inside the nuclear power plant with 2 experiments that are developing technology and exploring the frontiers of particle science. This facility has a large potential to boost the Latin American science, because it can be used by everyone. It's just to organize and to, let's say, to share the space, and who knows, to also install another lab inside the power plant, because people are from electronuclear, they are collaborating a lot. So takeaway message, this facility has to be explored by us, as because we have a very cheap nuclear, a very cheap particle source that it's there, it's for free, okay? You don't have to spend just $1 to have the neutrinos. So we do hope that the neutrino lab in Angra dos Reis can insert Latin America in the world map of research facilities in particle physics. Okay, so thank you. Sorry about the time.
No problem. We'll have time for maybe a question. One or two quick questions.
I have a question. Very nice talk. It's just curiosity. So you can detect if the reactor is on and off.
Yes.
The question is, can you also say something about the power of the reactor when it's on?
Not now. So probably with the upgrades, we can try to do this kind of measurement because up to now, we have some idea about the power delivered by the reactor, but sometimes the operator doesn't show us what is happening inside.
Yes.
So sometimes we have small pictures of the system, but it's not only for that. We have to improve the sensitivity of the detector in counting rate, because in previous analysis, using only counting rate, the fluctuations show to us that was not possible to say it's on or it's off. So we have to rely on the spectrum. And I mean, probably with improvements and rejecting a more effective background rejection, we can try to do this kind of monitoring.
There is a question from Carla. Go ahead, Carla.
Hello, Ernesto. Nice talk.
Hi.
I didn't know that you are abandoned the inverse beta decay to move to the 7. This is nice. So this sensor is is similar to Ricochet that is being planned to be installed next year in France. How the timeline of develop this in Brazil match with these efforts? Do you think that you will be competitive in this sense? Because as far as I remember, Ricochet is very near the core of the reactor, and we are at 30 meters.
Yes, so my answer to you is we are just starting to make these discussions, Carla. So our colleague, Pedro, he is a member of the CREST collaboration, and he knows about the Ricochet and Nucleus and all the technical difficulties and whatever. So in any case, in our discussions, we see that it's possible to make the development based on the known technology that people are using in these experiments and these underground experiments. And so, as I said to you, in a first glance, it seems that the difficulty is to install it and make it work inside the container, in our container. So I think that with the knowledge that Pedro has about the construction of these detectors, is not let's say, I think that in 5 years we can make the project, as I said, and probably after this timeline, think about to build prototypes and whatever.
I see. Thanks. So let me make a publicity, by the way, to invite you and Pedro to the next year. We will have the Magnificent Sevens, that is the 7th conference that we have in the world in Rio de Janeiro in CBPF. So we're very happy of that, and it's a very nice place where we can discuss all this and the efforts and the community collaboration. Thank you, Ernesto.
Okay, thanks, Carla.
Right, so we are a bit over time, so let's thank Ernesto. Thank you. And next we have Rafael Batista. He's gonna tell us about grant. Rafael?
Yeah. Hello, can you hear me?
Yes, we can hear you.
Okay, let me share my screen then.
You have 20 minutes. I will try to remind you.
Okay, I assume you are seeing the right screen. Yes, I can see it. Okay. So, hello everyone. My name is Rafael Batista, and today I'm going to give you a brief update on what I've presented in the previous edition of this meeting a few years ago, I think 2020, 2021, I don't recall. And I'm going to describe our recent activities on the Giant Radio Array for Neutrino Detection grant. Just to mention this, I'm presenting on behalf of several people from Latin American countries, from Brazil, and from Argentina as well, and on behalf of the whole collaboration. So just a quick recall for those of you who have never heard about GRAND before. GRAND is the Giant Radio Array for Neutrino Detection. So it's an upcoming high energy, or better, ultra high energy neutrino experiment that we have been working on for the past few years. And one of its main goals is to do neutrino astronomy at ultra high energies, which means that that tends to be 18 electron volts, more or less, overlapping with the energy range of ultra high energy cosmic rays, for example, and so on. But we can also do many other things, which include neutrino physics. We can study fundamental physics, physics beyond the standard model. And using the same setup with the same type of detector, we can also do some type of cosmology studies, in particular radio astronomy, because we have an array of radio antennas as well. So the primary goal is really to do this more astrophysical part, is to study astrophysical sources of ultra high energy neutrinos, high and ultra high energy neutrinos, and also to study cosmogenic neutrinos. And as I said, the secondary goals are these more cosmology and radio astronomy oriented science targets. So the main science case of GRAND, being the search for ultra high energy neutrinos, we can distinguish between two types of possible sources that we are interested in. The first one would be to study neutrino sources themselves. So just look at different types of astrophysical objects that could produce neutrinos with very, very high energy and see what we can learn from that. So this is essentially neutrino astronomy. But we can also do cosmogenic neutrinos. So cosmogenic neutrinos are those neutrinos that are produced when we have cosmic rays of ultra high energy traveling through the universe and interacting with pervasive photon fields like the CMB, the cosmic microwave background, or the extragalactic background light, and so on. So these are the two main types of neutrino targets, astrophysical targets that we are looking for. But ultimately, we are designing the experiment so that GRAND can be a discovery instrument. These neutrinos, so the highest energy neutrinos that have been discovered so far, are those by ice cube with PeV energies or so. And here we are really trying to push the energy, limit to higher energy to really detect neutrinos with 10 to the 16, 10 to the 17, or 10 to the 18 electron volts and see what we can learn from them. So the detection principle of GRAND is the following. Essentially, we have an array of antennas. So the antennas are those like here, like this one here at the bottom. They are about 4. This is not accurate, but it's a few meters high. And the idea is the following. If we have just a standard cosmic ray, for example, the standard cosmic ray will produce an air shower. And during the air shower development through the atmosphere, there will be some emission of electromagnetic radiation in the radio band. And these can be detected by our antennas, which operate more or less between the range of 50 to 200 megahertz. But for neutrinos, that's the most interesting part, is that the way that we have to distribute our detector in the world, we have to take into account the topology. We need to have some mountains around to increase the probability that these neutrinos will interact with this target, with these mountains. And once, for example, a tau neutrino interacts with a mountain, as you can see here on the right-hand side of the figure, the tau neutrino will produce a tau lepton. And that these extremely high energies, the tau lepton, will live for a time comparable to a distance of tens of kilometers. And if we have an array of antennas over a distance of 10 or 20 or 30 kilometers or so, we can actually detect the radio emission due to the decay of the tau particle produced by a tau neutrino. So this is the principle that we will employ in GRAND. And the antennas that we are talking about, this is just a cartoon of the design that we have. It's like a type of antenna that has 3 arms, one in the X direction, the other one in the Y direction, and a vertical one. And we also have a solar panel at the bottom. We have like GPS information for each antenna. We have the front end board electronics below this solar panel, as you can see here. And we also have some kind of communication device, Wi-Fi, to transmit the data that we have. And what we expect to see is that for symmetry reasons, the X and the Y arms of the antenna, which are parallel to the ground, they will behave more or less in the same way. So this is what's being shown here at the bottom left plot called antenna X arm. So what we are seeing here is the more or less the effective antenna length, so the antenna response for different combinations of zenith angle and azimuth angle for the X and by symmetry reasons, the Y arms of the antenna. We also have the Z arm of the antenna, which behaves slightly different in zenith and in azimuth because it's pointing upward. And this is just the transfer function, which is what we expect to get from at the end. So once the radio signal reaches our antenna, it becomes just a current, which is detected. And this is an example that we have here for the different types of the arms that we have for the X, for the Y, and for the Z arms as a function of the frequency of this radio emission between 50 and 200 something megahertz. An example of the signal can be seen here. So this is more or less, this is a simulation that we have. We have the latitude and the longitude, and this is the prototype we are currently deploying called Grand Proto 300. We have several antennas which are indicated by this dot here. This is not final yet. This is just a simulation. Okay, we are still deploying the antennas. And we have one particle hitting the ground here at this yellow star point, producing a signal. And what we see in our array, which is this hexagonal array shown here at the left and on the right, it's shown in the color scale here on the right hand side as time, right? We have a radio signal reaching different detection units at different times. Okay, this is just a simulation-based example so that you can understand the principle of GRAND. And we have, as a signal from this previous plot that I've shown here, we have, of course, we get the electric signal for the 3 different arms of the antenna for the X, the Y, and the Z arm. And these 3 different components is what we are seeing here on this left plot and and individually on this right-hand side plot. Right. On the right-hand side plots, what we can see is that the solid line is essentially just an amplified version of the voltage that reaches each antenna. And the dashed line is if we include the radio signal, the radio noise of our own galaxy, which is always present there, which has to be removed for our studies. And the same for the Y port, for the Y arm of the antenna, and for the Z. So this is an example of a simulation that we have been deploying. So we have a full pipeline actually that we have been used to analyze and to forecast the capabilities of our experiment to detect ultra-high energy neutrinos. So for any ultra-high energy neutrino or ultra-high energy cosmic ray or ultra-high energy photon that reaches the atmosphere and that produces a radio signal, we have different antenna responses, which is just plugged in, which is built into this code, right? And we have this database that's built with these different codes called Danton, Corias, or Xyris for the radio emission in particular. And we can forecast the capabilities of the experiment. So what's the expected voltage that we get for each radio signal that reaches the antenna, and so on. Right, I won't go into detail here too much. If you're interested, in the end, I can answer questions about this, but I think you're probably all tired because we are over time. So we have currently three prototypes operating. One of them, and probably I would say the smallest one, which is called Grand at Nancy. It's here in France, at the Nancy Radio Observatory. It's just 4 antennas like this, spread as if you look at this right-hand side plot around these green lines, at the end of these green lines. And the goal of this prototype is essentially just to perform hardware and trigger tests. We also have another experiment which is running, another prototype which is running, which is called GRAM at Auger. It's running in Malargüe at the Pierre Auger Observatory site. Actually, it's running in the AERA site. AERA is the Auger Engineering Radio Array, for those of you who are not familiar with it. So we are using the Auger infrastructure in Argentina to actually calibrate our antennas and our hardware and our instruments overall. Right now, we have 10 detection units, that means 10 antennas deployed, running in Argentina. And we have some people working there in this picture on the field, right? People deploying the antenna. And the Grand Auger is being really used at the moment as a benchmark for hardware and to perform some tests of the instrument, and if we can remove some background and this type of study. And so that you know that this is an international effort. You have people here from Brazil. We have like João Torres and Beatriz, PhD students from UFRJ in Rio. We have Matias Tueros here from Argentina deploying the antennas. And the data transmission here is being done at the moment using 4G technology in each one of these antennas, which is pretty cool because we can all access the data in more or less in real time from here, because whenever we have a trigger at a certain level, it's registered and we can just track the event and study it from far away. And we are right now trying to do this type of event-by-event comparison with Auger, comparing the detections of our antennas with Auger detection. And this is pretty very important for to test the performance of this type of technique. And the main prototype that we have, that we are currently deploying, we just about to finish commissioning, and we are currently starting to deploy this year. This summer we started. It's Grand Proto 300. It was recently approved by Chinese officials. It's being deployed in Dongguan in China. It's a province in central northern China. And the idea is to have each one of these pink dots that you can barely see is one of these antennas shown here on the left. We will have 230 of such antennas separated by more or less 1 kilometer from one another. And in some parts, we also have an infill, a denser infill to extend the energy range with an inter-antenna separation of 0.5 kilometers. This was really recently approved. We already have several antennas there. We expect to have at around 80 antennas probably by the end of the fall, the Northern Hemisphere fall, I should say, or the spring for people in South America. Okay, and Grand Proto 300, it's really, even though it's a prototype, it's a standalone instrument that can do a lot of interesting science on its own. It has a very rich science case. It can detect particles in the energy range between 30 PeV and 3 EV. It's very unlikely that at this stage we'll be able to get some meaningful results for neutrinos, because we need a much larger array to detect neutrinos. But we can do a lot of cosmic ray studies in this energy range. We can study the transition between galactic and extragalactic cosmic rays. For instance, depending if we get funding for additional type of units, we can add some particle detectors to improve our discrimination and also detect some gamma rays and so on. So I would say that with this intermediate state that we have 80 antennas, which is supposed to happen soon, before we get to Grand Proto 300, we can already do some actual science, and we can do radio astronomy. You can see fast radio bursts with these antennas as well. Although this is not the traditional type of astronomy that people are used to. It's not like the radio astronomy dishes that people usually use to do radio astronomy. This is another concept, and it works, right? We can detect fast radio bursts with this type of setup as well. So GRAND and the prototype, GRAND Proto 300, it's not just an instrument for astroparticle physics at the highest energies. It's an instrument also for radio astronomy and for cosmology. And just a quick note on the prototype performances, GRAND Proto 300, we installed a beacon here at this orange point here on this top left figure, right? And I won't go into the details here, but bottom line is that we can, using these antennas, these detection units represented here on this plot by the blue circles, we can actually reconstruct the position of the beacon within 10 meters of error, which is pretty good. So this ultimately is proving our points that we can reconstruct an artificial signal emitted by a beacon with a very good directional precision of 10 meters here in this case. And we are also doing tests in the OGE site, as I said before. So this is a Google Earth view of part of the near Malargüe in Argentina, where the OGE engineering radio array is located. And we have some GRAND antennas there, those 10 antennas that I mentioned before. And we are also performing some tests, and we actually have been detecting some background radio signals here, coming from this village called El Sosneado. And the agreement is very good. So the precision, the location of this village is exactly the location of this new background source that we are identifying, which is extremely useful, such that we can identify noises and remove it from our signal in the end. So the GRAND collaboration is an international collaboration with 120 members, 45 institutions from 14 countries. The Latin American countries that are involved are Argentina and Brazil, and they have been taking leadership roles. We have task forces being led by people from these countries. The institutions that are involved are the Instituto de Física de La Plata in Argentina, the Federal University of Rio, and CEFET in Rio as well.
2 minutes, Rafael.
Yeah, thank you. So I'm just wrapping up now then. So the timeline for the experiment is we are right now at the prototyping phase. And then after we finish the prototype with GRAND Proto 300, we are aiming for to extend to have 10,000 antennas forming this what we call GRAND 10K. And then the idea is to deploy multiple GRAND 10Ks around the world when the technique is already matured and we understand everything, such that we can build an even larger array spread around the world to really do ultra-high energy neutrino astronomy. And I'd just like to finish, before I finish in 1 minute here, to mention an idea that we have been, some people have been considering. So GRAND has been partnering up with this other experiment called Beacon, which is a type of phased array for neutrino detection. A very similar principle to GRAND, but it's phased. So yeah, it also it's altitude dependent. And the Argentinian team at ITEDA, led by Federico Sanchez, they are right now considering prospecting locations around the region of San Juan in Argentina to really consider deploying this hybrid type of array, which is not only a GRAND type of array, but also a beacon type of array with another type of antenna, which could lead to some better performance for a neutrino astronomy, although that's, a better pointing precision and so on. So the idea is to really, in this case, to consider building a hybrid GRAND/beacon, which is another project array. And Argentina is one of the most interesting sites. And the Argentinian community is strongly supporting this effort right now. The international consortia of the GRAND and Beacon, we are trying actually to raise some funds to really start playing with this idea, to start the site survey this year and do some site monitoring over the course of next year, and maybe build some prototypes in 2026 for in the future have a full deployment of around 2030 of this full HERON, Hybrid Elevated Radio Observatory for Neutrinos, which is a new type of idea within the umbrella of a grant. And I think I ran out of time, so I'll stop here. Thank you.
Thank you. Questions for Rafael?
A quick question. Rafael, thanks for our talk. Is TAMBO in Peru something similar to this or not?
Yeah. The idea of TAMBO is very similar to what I just described here. It's to use the slope of the mountain as an advantage to detect to get the neutrinos. However, TAMBO is not a radio detector. TAMBO is a particle detector, as far as I know. Carlos is not here to answer, but to my knowledge, it's a particle detector, not a radio detector. But the idea is really to increase the sensitivity of your instrument by tilting it along the mountain and using the interaction of the shower with the mountain on the other side in your favor to increase your signal. So you really have to look for very specific topologies, for very specific sites around the world.
Okay, thank you.
Okay, any other very quick question?
Yes, thanks a lot, Rafael. Concerning the grant 200K, so you mean that you can have 20 sites on the world with the same conditions of very low background as in the deserts in China?
Okay, I don't think we can have 20 sites of 10,000 with the same conditions, but as long as we understand how to remove the background, we can just replicate this 10K array in several sites, as long as we understand how to remove this background. If there is no new type of background that we don't know about, which is very unlikely. There are places with a higher background, places with a lower background, but I think it's very unlikely that conditions are going to be so different, right? I think the problem here is really more of a logistical problem and financial problem to really get these 20 subarrays of 10K built in the end.
Okay, let's thank Rafael again.
Thank you.
And we have 12 minutes or 11 minutes till 4:30, so we better get